Hey everyone, welcome back. Today we're diving into something pretty critical in the world of AI, especially as it gets, well, more and more integrated into everything we do. The paper is called Hierarchical Fallback Architecture for High-Risk Online Machine Learning Inference. Catchy title, right?
Yeah, well, academics.
But honestly, the name kind of gets to the heart of it. It's all about making sure those AI systems, especially the ones making big decisions, don't just fall apart if something unexpected happens.
That's right. Think of it like a safety net. You know how important those are, right?
Totally. And this idea, this system-level robustness, is super relevant in something called open banking.
Which, just to be clear, is basically giving third-party apps access to your financial data. So they can do things like give you personalized financial advice or manage your money.
It's a pretty big deal in finance right now. But, I mean, more connections, more data, doesn't that also mean more chances for things to go wrong?
Oh, absolutely. That's a huge part of what makes this paper so interesting. It tackles that head on.
And they really drive home why this matters to, well, everyone. Think about it. You're online, buying something, and the bank's trying to decide if it's legit or maybe fraud, all in real time.
And that system's pulling data from all over the place, right? Your bank, your credit score, maybe even checking for any fraud trends that are happening that very second.
So many moving parts.
Yeah.
What if your bank system has a hiccup? What if some of that data gets messed up?
Things can get really messy really fast. The system might just not be able to do its job. So maybe a legitimate purchase gets declined or, and this is the scary part, a fraudulent one slips through.
I can see why they call this high risk.
No kidding. The financial impact, the security risks, it's huge. Robustness isn't just a nice to have here. It's a must have.
And it's not just about the AI model itself messing up. Although, I mean, that can happen too.
Sure, but this paper looks at the entire ecosystem, the data coming in, the servers doing the work, the software that connects everything. It's like, if one little thing breaks,
the whole system could come crashing down.
And that's where this hierarchical fallback architecture comes in. It's kind of genius, actually.
Lay it on us. What is this hierarchical fallback architecture?
It's like, imagine a chain of command.
Okay, I'm following.
You've got your main strategy, your best troops, but you also have backup plans, reserve units, ready to go if things get hairy.
So, like, if the main AI model, the star player, can't do its thing, there's a backup ready to step in.
Exactly. Picture this. Back to that online purchase, right? But this time, the system needs info from your bank, but oh no, the bank system is down.
Oh.
Instead of just freezing up, this architecture has a backup model specifically trained without that bank data. It can still assess the risk, maybe not perfectly.
But it's better than nothing, right? Like having a second phone number in case your main contact is unreachable.
Right. It's not ideal, but it keeps things moving, and that's just the first fallback.
There's more.
Oh yeah. What if the main model itself is acting up? Maybe it's super slow or hitting some error. Instead of giving up, the system tries running it again, but with some rules, like time limits, error thresholds, things like that.
So you're basically saying, all right, one more try, but if you don't shape up,
we're moving on. We've got stuff to do. And if that doesn't work, well, that's when we break out the emergency plan.
The last resort.
Think of it as the break glass in case of emergency model. Simpler, less accurate, but it's always there. Like, having a basic compass when your fancy GPS freaks out.
So it's like function over perfection when things are really bad, but does this actually work in the real world? It all sounds good in theory.
That's where the open banking case study comes in. These researchers teamed up with Trustly. They handle millions of payments, all using open banking.
Millions.
Yeah, and here's the thing. Trustly connects to almost every U.S. financial institution. Their system. Super complex. Like, they threw everything at it. Data outages, server crashes, you name it. Even simulated those huge traffic spikes you get during, like, the Super Bowl.
Putting it through the ringer. So how did it do?
It held up, kept things running, even when parts of the system were down. Sure, there were some differences in performance between the main model and the fallbacks, especially when they had to go to that super basic one.
A trade-off, though.
You could say that. Accepting a bit less accuracy in extreme cases to make sure the system keeps working, which, let's face it, is way better than the alternative.
Right, because a total system meltdown, that could be catastrophic. So this hierarchical fallback architecture, it's not about replacing the main system, it's about
having that safety net, making sure there's always something there to catch you if you fall.
Smart. And before we move on to part 2, where we dig into the history behind all this, I want to touch on something we were talking about before the show. This idea of self-healing AI.
Oh, yeah. Now that's where things get really interesting. What if instead of pre-programmed backups, we had AI that could just reconfigure itself when things go wrong?
Whoa, like AI that can sense a problem and just fix itself.
Exactly. Think about how our brains adapt when we're tired or stressed. What if we could do that with AI?
That would be a game changer, not just in finance, but healthcare, transportation. The possibilities are huge. But that's a discussion for part 3.
For now, let's take a step back and look at how we even got here. The earlier attempts at making AI systems robust and why they weren't quite enough. It's kind of cool to look back at how we thought about robustness in AI. Like early on, it was all about making the AI model itself super tough.
Like trying to predict every possible problem and bake in a solution.
Yeah, basically. Make it handle noisy data, missing values, weird inputs, all that real-world messiness.
I can see the logic there.
And we made some real progress. There's this technique called adversarial training. It's like,
Yeah.
imagine putting your AI model through boot camp, but the drill sergeant is another AI trying to break it.
Whoa, AI versus AI.
Exactly. This attacker AI is trying to find weak spots, things that fool the model. The idea is expose it to those vulnerabilities during training so it learns to fight back.
Clever. But the paper says even with all that, true robustness is tough to guarantee. Why is that?
Well, machine learning can get really complex, especially with deep learning. We're talking models with millions, sometimes billions of parameters. It's like
A billion moving parts.
worse. It's almost impossible to know exactly how they'll behave in every situation, let alone predict every single thing that could go wrong.
Like trying to predict where a single leaf will land when it falls from a tree.
Perfect analogy. Too many variables, too much chaos. And the paper points out, even if we could make models perfectly robust,
It wouldn't solve every problem.
nope, because it's not just about the model, it's the whole system. Data pipelines, servers, software, anything can break.
Right, that weakest link problem.
Exactly. That's why this paper's focus on system-level robustness is so important. The model is just one piece of the puzzle.
Which brings us back to those fallback models, like having a plan B and C and D ready to go.
It's about gracefully degrading, Maybe the output isn't perfect, but at least it's something.
The break glass in case of emergency option, like those backup generators people have for their houses,
Yep.
right?
Exactly. Power goes out. You might not be running everything at full blast, but you still got lights. You can still make coffee.
Essentials.
Yeah.
And I like how the paper actually measured the performance differences in that Trustly study. Real world data, not just theory.
Oh, yeah. They found the biggest difference was with that simplest fallback model, the one hard-coded into the server.
Hard-coded.
Built right in, like the most basic, bare-bones solution. Accuracy took a hit, but they said that scenario only happened in like 0.1% of cases.
So a tiny fraction of the time, a calculated risk.
Right, accepting a little less accuracy in super rare cases to keep the system running smoothly. Way better than a total crash.
Absolutely. And they really stressed their system, didn't they? Like simulated all kinds of chaos.
Oh yeah, they went all out. Server outages, network problems, even those crazy traffic spikes you get during big events.
Right.
They wanted to see if it would break.
And it held up.
It did. Which is pretty strong evidence that this approach works. Don't just build robust models, build robust systems. It's a different way of thinking.
It's like moving from a model-centric view to a system-centric view.
Exactly. For a long time, it was all about accuracy, making the model better and better.
But now, as AI gets used in more and more important stuff like finance, healthcare,
Accuracy isn't enough. We need to think about how it's deployed, how it interacts with everything else, how it behaves in the real world, which is messy and unpredictable.
so it's not just about performance, it's also about reliability, scalability, security, the whole package.
Couldn't have said it better myself. And that brings us back to that novel notions idea we were kicking around. Self-healing AI.
Right. What if, instead of pre-programmed backups, we had AI systems that could actually diagnose and repair themselves? Welcome back, everyone. We've been talking about making AI systems tougher, more reliable, especially when the stakes are high. But now time to get a little speculative, a little out there. It's our novel notion segment where we take the paper's ideas and, well, run with them. And this paper got us thinking, what about AI that can heal itself?
Self-healing AI, yeah. It's pushing the limits of what we can even imagine AI doing right now. Like, think about it. A system that not only knows when something's wrong, but figures out what it is and fixes it, all on its own.
That's like having an expert mechanic under the hood, constantly checking for problems. Except the mechanic eye the AI.
Right. We talked about those fallback models, the backups. They're great, but you have to program them ahead of time, you know? You have to predict what could go wrong. Self-healing AI, that's different. It could adapt to anything.
So it's not just reacting, it's being proactive, constantly watching itself, catching problems before they even happen.
Exactly. Like, think about our bodies, how they handle injuries, illnesses.
Oh, good point. Our immune system, fighting off threats, our brains rewiring themselves after an injury.
Nature's been working on self-healing for a long time, right? Billions of years to perfect it.
So the question is, can we learn from that? Can we build AI that's as resilient as, say, our immune system?
That's the big challenge, and some people are already working on it. It's early days, but super exciting stuff.
Okay, let's be real. We're not talking about AI growing back a lost arm or something. But what if it could spot weird data, fix errors in its code, maybe even patch itself?
That's more like it. And even those things would be huge for making critical systems more reliable. Imagine self-driving cars that can fix their own sensor problems, or financial systems stopping fraud before it even happens.
Powerful stuff, but also kind of scary, right? If AI is going to be that smart, that independent.
We got to be careful, really careful. We need rules, transparency, human oversight. We can't just let self-healing AI loose without thinking about the consequences.
It's a reminder that, as cool as this technology is, we got to think about the ethics too. Make sure AI is used for good.
Absolutely.
Well, this has been a wild ride. From fallback models to self-healing AI, we've covered a lot.
We have.
And as always, keep those brains buzzing, folks. Think about these ideas, talk about them. Let's figure out the future of AI together. Until next time.